Hi, my name is Ching and welcome back to Data Structures in C++. In the previous lecture, we talked about binary search trees and the problems with using them. One main disadvantage of using binary search trees is that the tree can cause performance issues when the tree is not balanced. But what exactly do we have to balance? The answer to that is the height of the tree. How do we do that exactly? In this lecture, we'll talk about how to create a balanced binary search tree and how to rebalance it after inserting or deleting a node. So why should we balance a tree to begin with? Well, the runtime complexity of a lot of methods will depend on the height of the tree, and we'll need to minimize the height of the tree to get quicker results. Let's say that a tree has n nodes. The best case runtime or the lowest height would be O log n. And the worst runtime, or the biggest height, would be ON. So to make sure we get the best performance, we must maintain the balance of the tree, such that the height will stay at O log n. Here are two examples of unbalanced trees. In one example of a balanced tree, let's start with the first unbalanced tree. It looks symmetrical, so it should be balanced, right? Well, the answer is no, because even though it is symmetrical at the root, the left and right subtrees are not symmetrical. For example, if we look at the left subtree, it only has a right child. This tree is unbalanced starting from the root. Now let's formally define what makes a balanced tree. A tree can be balanced by a few different criteria. In this course, we only care about the first one, which is by comparing the height of the subtrees. More specifically, we'll talk about AVL trees. If the tree is balanced, such as this example, then moving down from the root at each level, the number of nodes will double. So, as we learned in the complexity analysis lecture, if we double the number log n times, it will become n. So, a balanced tree can guarantee its height is O log n. Please note that a balanced tree doesn't always mean the heights of the subtrees are exactly the same. We will talk about this later. But the height is still in the order of log n. Before we dive into AVL trees, let's look at some basic examples. We'd start with a binary search tree which only contains two nodes, 3 and 2. In this BST, 2 is the left child of 3. Now let's add a new value 1 to this BST. The node 1 will become node 2's left child, and in this BST, it has two levels of children. So it doesn't have any right children. This is called the left-left imbalance. It is equivalent to a linked list. So this can be easily rebalanced by a clockwise rotation. After that, the node 2 will become the new root, and node 3 being its right child. So node 1 still stays at node 2's left child. So now this tree is balanced. Similarly, if we have a mirrored scenario, which is a right-right imbalance, we will do a counterclockwise rotation. We'll skip that here since you get the main idea. So here's the second base case. Assuming we have this BST, with node 3 being the root and node 1 being the left child, now we insert a new node with the value 2. The node 2 will become the right child of node 1 here. So this creates a left-right imbalance because from the root node 3, it only has a left child, which in turn only has a right child. So you see how the name kind of fits with how the scenario looks like. It's a left-right. So to rebalance it, we note 2 is the middle value. So it will be promoted to the new root. So 2 will go here to the root. 1 will turn into 2's left child, and 3 will turn into 2's right child. So this is the exact same balanced binary search tree as we saw in our last case. So same as the last example, there's a mirrored scenario. We have a right-left imbalance, and the operations will be similar. So including mirrored scenarios, we have 4 base cases in total. We will use them in implementing AVL trees. So far, I haven't formally defined what an AVL tree is, but we'll do it right here. So AVL trees are named after 2 mathematicians with the first letters of their last names, A, V, and L. So as I mentioned before, depending on how many nodes the tree has, its left and right subtrees may not have the exact same height. So for example, if a BST only has 2 nodes, then one subtree has a single node and the other subtree is empty. But it is still called balanced because there is no way to make it more balanced. With that in mind, let's define the AVL trees. There are 2 points here. First, the height difference between the left and right subtrees is at most 1, so it can either be 0 or 1. Second, the AVL tree is also defined recursively, which means both the subtrees are themselves AVL trees. For example, this tree is AVL balanced. To make the height mathematically consistent, we define the height of an empty tree to be the value of -1, and the height of a single node is 0. Obviously, only insertion or erase can possibly change the height of a tree. Let's see how an insertion could cause imbalance. Let's use the same tree from the last slide, which is AVL balanced. But we noticed at the node 17, its left subtree is empty. So the height of its left subtree is -1. So let's move on. And its right subtree contains only a single node. Thus, the height of the right subtree is 0. So we know the height difference between the left and right subtree is 1. So according to the AVL tree definition, the subtree with the root node 17 is still balanced. So if we wanted to break this balance, what we need is to increase the height of the right subtree by 1, which means we can insert a new node as either the left or the right child of the node 27. So that would break the balance of this tree. So we'll need to fix that. Suppose we insert the new node 23. So it will become the left child of the node 27, because if we look through all of this, it would fit right here. So it will make the node 17 unbalanced, unfortunately, but it will also increase the heights of each of the subtrees from here to the root by 1. So not every node along this path will be unbalanced. For example, the node 12 is still balanced because the height difference between the left and right subtrees is now 1. But the node 23 is unbalanced because the left subtree has the height of 3 and the right subtree has the height of 1. It may seem like we need to fix multiple unbalanced nodes in this tree. But the truth is that if we fix the lowest unbalanced node, then higher ones will be balanced automatically. We'll see why in a second. Let's start from the unbalanced tree. As we said, we will start with the lowest unbalanced node, which is the node 17. We can single out the subtree with the node 17. So this is the right-left imbalance because the root node 17 has a single right child. which in turn has a single left child. To rebalance the subtree, we know the middle value is the bottom node, which is 23, so we promote that node as the new root. After rebalancing, the subtree becomes this. Then put it back to replace the original subtree. Incidentally, the node 36 also becomes balanced. However, the scenarios are not always that simple. Let's look at more general examples. So, after we insert 6, the height of all the nodes along the path to the root is increased by 1. But after checking each node, only the root node 36 is unbalanced. So this is not a simple subtree with only 3 nodes. So how do we rebalance it? So to make this more general, we will first describe the existing AVL tree using a template. In this template, each triangle represents a balanced tree of height h. For example, BL means the left subtree of the node B, and BR means the right subtree of node B. FR means the right subtree of the node F. Now we add a new node below the tree BL. After inserting the node A into this tree, we can see the node B is still balanced because the height difference from its left and right subtrees is 1. But the node F becomes unbalanced because the height of the left subtree is now h plus 2, and the height of the right subtree is h. Then the difference is 2. Using the template, the triangle can be a subtree with 0 nodes, 1 node, or more, as shown in these 3 examples respectively. By adding the new node 7, the tree becomes unbalanced at the node 17. Now let's see how we can rebalance it. First, we break apart those 3 pointers. Let's ignore the subtree BR for a second. The node F is a left-left in balance with the node B, which is in the middle. So it can be rebalanced by a clockwise rotation. After that, the node B becomes the new root, and node F becomes the right child. The subtree BL and FR still keep connected. Now we reconnect the subtree BR as the left child of the node F, and reconnect the node F's parent to the node B. We can check the heights for each subtree now. It is all balanced. With this general case, now we can answer the previous question. If there are multiple ancestors becoming unbalanced, do we still need to fix them one by one? Fortunately, the answer is no, because previously, the height of this whole subtree is h plus 2. And after inserting a new node and rebalancing, the height is still h plus 2. So nothing has been changed beyond this subtree. Now let's go back to work on our original example. After inserting 6, we can rebalance the tree by following the exact operations. Those are the 3 additional examples which fit the template where the triangle represents an empty subtree, a single node subtree, and a balanced subtree, respectively from the top to the bottom. Then the node 7 is inserted and the right side shows the rebalanced trees. So far, in the previous general case, we add a new node at the bottom of BL, the left subtree of the node B. But what if the new node is added at the bottom of BR, the right subtree of node B? This will make the node F unbalanced. Here are some examples to fit this template by adding the new node 14. This seems to be very similar to the previous case, but actually needs a few more steps. First, let's see why our last solution doesn't work in this case. After the same operations, the node F is rebalanced, but the node B becomes unbalanced. If the previous solution doesn't work here, it means we have to divide the subtree BR into smaller pieces. If we use D to represent the root node of BR, then its two subtrees can be represented as DL and DR. Both of them will have the height of h minus 1. Otherwise, the lowest unbalanced node will be the node D. Now we can insert a new node at either DL or DR's bottom to make the node F unbalanced. To fix it, we first break up those pointers. Then we look at the node F, B, and D. It's a left-right imbalance. For left-right imbalances, all we need to do is promote the bottom node as the new root. Then the node B and F will become the left and right child. Now we reconnect the other broken pointers. By checking the height for each subtree, we can verify this whole subtree is now balanced. Again, these rebalancing operations are local to this subtree because after inserting the new node and rebalancing, the height of the whole subtree is still h plus 2. Nothing has been changed beyond the subtree. Here are some additional examples we showed earlier which fit the template. After inserting the new node 14, the right column shows the rebalanced subtrees. So far, we only talked about two general cases, but we can easily mirror those two cases, and then we get another two. All operations can be mirrored too, so we will skip them here. So in summary, to minimize the height of a binary search tree, we need to balance it. One way to balance it is the AVL tree. AVL trees are rebalanced each time a new node is inserted or erased. You can't rebalance it altogether after you insert or erase multiple nodes because all the techniques assume we start with a balanced tree. We talked about two general cases, but with mirrored cases, we have four. We can also use the same techniques to rebalance after a erase, but the imbalance may propagate, so it may require rebalancing a few times. We'll skip those in this course. This concludes today's lecture. Have fun and happy coding. I'll see you next time. Bye bye.